Hey there, fellow philosophy fans. Ready for a deep dive?
Always.
Okay, good, because today we're tackling a concept that might just twist your brain a little bit.
Oh, I'm intrigued. Lay it on me.
It's the nature of space-time itself.
Space-time, huh? Always a fun one.
Yeah. And we're using the Stanford Encyclopedia of Philosophy's entry on something called the whole argument as our guide.
Hold argument. Okay, you've officially got my attention.
So to kick things off, think about this. Is space-time like a substance? Like a canvas, just waiting for a painting?
A canvas.
Or is it more like something that only exists because of the stuff in it? Like parenthood. You can't have parenthood without, well, parents and children.
Okay, interesting analogy. I see where you're going with this.
Right. So that's basically what this whole deep dive is about, figuring out if space-time is a thing in itself or just like a side effect of all the stuff happening in the universe.
It's a question that has puzzled philosophers and physicists for ages.
And get this, the argument was actually first thought up by Einstein.
Einstein. Really?
Yeah, back in 1913.
Wow, that's pretty amazing.
He was working on his theory of general relativity, but he was struggling with it.
Yeah, even geniuses have their struggles. It just goes to show how mind-boggling these concepts can be.
Right. And he actually thought for a bit that this whole argument, disproved general relativity entirely.
It really highlights how much our understanding of the universe has evolved over time and how we have to constantly reevaluate our assumptions.
Absolutely. And speaking of assumptions, let's talk about general covariance for a second.
Oh, yeah, that's a big one.
Because, our listener is a philosophy enthusiast. They might already know all about it, but for those of us who maybe haven't taken a physics class lately, what does that even mean?
Sure, general covariance, at its heart, it means the laws of physics shouldn't change based on how you're looking at them.
Okay.
Like, imagine translating a philosophical text, right?
Yeah.
The ideas stay the same even if the words are different.
Oh. So, the rules of the game don't change just because you switch seats?
Exactly. It's about the underlying meaning, not just the way we represent it.
Uh-huh. Makes sense.
And to understand this whole argument, we need to break down how we think about space-time in modern physics. There are two main pieces to the puzzle.
Okay, hit me.
First, there's this thing called a manifold of events.
Manifold of events. Okay, that sounds pretty abstract. What's that all about?
Think of it like a map.
A map. Okay.
But instead of countries, each point on the map represents a specific location in space at a specific time. Like every single event that's ever happened or will ever happen has its own point on this giant cosmic map.
Wow. So, it's a map of every when and where in the universe.
Pretty much.
Okay, got it. So we have our giant map, our manifold. What's the other piece?
The other piece is the metric field. This is where things get really fascinating.
Oh, good. I love fascinating. Tell me more.
So the metric field is what gives the manifold its shape. It tells us about distances, how time flows, and even gravity. Imagine taking that flat map and stretching it and warping it. That's how we represent gravity bending space-time.
So the metric field is what turns our flat map into a 3D model of the universe, with all the bumps and curves and stuff.
Precisely. And here's where general covariance gets really wild. We can actually rearrange the metric field and the matter within it, kind of like rearranging furniture in a room, without actually changing the underlying physics.
Wait, so you're saying we could move planets and stars around and the laws of physics would still be the same?
In a way, yeah, that's what active general covariance allows us to do. We can have different arrangements of the metric field and matter that still work within the laws of physics, but they have to connect smoothly at the edges, you know?
Okay, I think I'm following so far, but how does all this connect to the whole argument? What are these holes we're talking about?
That's the next step in our journey. We have to dive into these holes to really understand the implications of all this rearranging.
Okay, lead the way. I'm ready to jump down the rabbit hole.
All right, let's go. All right, so to understand these holes, we need to talk about what are called invariants in space-time theories.
Invariance, okay.
Yeah, so these are properties that stay the same no matter how you describe them, or how we move stuff around inside our hole.
So, are these invariants kind of like those universal constants we hear about in physics? The values that are always the same no matter where you are or how you're measuring things.
Yeah, that's a good way to think about it.
Like the speed of light, for example.
Right, exactly. The speed of light is an invariant, and so are things like distances along certain paths or the mass of a galaxy.
Huh. Okay, so even though we're messing with the arrangement inside the hole, these invariant properties stay the same.
Exactly, that's the key point, and that's where the whole argument really starts to get interesting, especially for people who believe that space-time is like a substance that exists on its own.
Okay, so for the substantivalists, as we like to call them in philosophy.
Right, the substantivalists. So if space-time is a substance, then these two versions of the universe, the one before the whole transformation and the one after, they have to be different in some way.
even though they look exactly the same.
Right. Even though all the measurable stuff, all the things we can actually observe are identical.
It's like, I don't know, having two paintings that look exactly the same, but the brushstrokes are different or something.
Yeah, that's a great analogy. And this is where things get a little tricky because if these two universes are different but we can't observe any difference, that leads to some pretty weird conclusions.
Oh, I love weird conclusions. Let's hear them.
Well, the first one is indeterminism.
Indeterminism. Okay.
Basically, if our laws of physics can't tell us which of these two arrangements is going to happen, then there's a kind of randomness in the universe that we don't usually see in other areas of physics.
Wait, so you're saying that even if we knew everything about the universe right now, we couldn't perfectly predict the future?
Well, yeah, that's kind of what it implies, because there might be multiple whole transformed versions of the future, all equally possible.
Huh, so much for a deterministic universe, right.
Right, and it gets even weirder, because the second conclusion is what's called unverifiability.
Unverifiability. Okay, another good word.
So if we can't actually observe any difference between these two arrangements, even in principle, then how do we know which one is the real one?
Whoa, so you're saying there might be, like, fundamental truths about the universe that we can never know?
Yeah, that's the implication. And that's a pretty tough pill to swallow, especially for a philosopher, because it makes you question what it even means for something to be real if we can never know it.
It really challenges our whole idea of what it means to know something, right?
Right, so you can see how this whole argument puts the substantivalists in a bit of a bind.
Yeah, they're kind of stuck between a rock and a hard place, huh?
They have to either accept this weird indeterminism or admit that there are things about the universe we can never know.
So what are their options then? Are there ways out of this dilemma?
There are, and the Stanford Encyclopedia of Philosophy actually outlines 5 main responses to the whole argument. One is to just give up on substantivalism entirely.
Okay, so no more space-time as a substance. What's the alternative?
Well, the alternative is what's called relationalism. It's the idea that space-time is just a network of relationships between things, not a thing in itself.
Interesting. So that's one option. What are the others?
Another option is to just accept the indeterminism. Some philosophers argue that it's not actually a problem.
So they're okay with a little randomness in the universe.
Yeah, they might argue that it doesn't actually undermine our understanding of the physical world.
Okay, that's two responses. What about the others? Any that try to, like, save substantivalism without accepting these less than ideal consequences?
Yeah, there are a couple. One is called metric essentialism. It's a pretty complex idea, but basically it says that the properties of things in space-time are essential to what those things are.
So, like, you can't change the properties of something without changing what it is.
Exactly. Like, imagine trying to change someone's personality without changing who they are as a person.
Okay, so that's metric essentialism. What about the other one?
The other one that tries to save substantivalism is called sophisticated substantivalism. And this one, it tries to find a way to distinguish between these different whole transformed universes without relying on essentialism.
How do they do that?
It involves looking at different ways of representing space-time mathematically and arguing that some representations are, like, more accurate than others, more true to the real structure of the universe.
Okay, I'm starting to see how complex this gets. So that's 4 responses. What's the 5th one?
The 5th one is kind of a different approach. It says that the whole argument isn't really a problem with space-time itself, it's a problem with how we're thinking about it.
Like a problem with our language or something?
Exactly. It's more of a mathematical or formalist approach. They might say we're taking our mathematical models too seriously, like confusing the map for the territory.
I see. So it's a reminder to be careful about how we interpret our scientific theories, to not get too caught up in the math and lose sight of the actual physics.
Right. But, all this talk about the whole argument makes me think about Einstein again.
Oh, yeah, he's the one who came up with it in the first place, right?
Exactly. And it's interesting because even though he formulated this argument that seems to challenge the idea of general covariance, he kept working on general relativity, which is, like, based on that very idea.
So how did he reconcile that? Did he ever address that apparent contradiction?
He did. Eventually, Einstein came to believe that the real, like, physical meaning of a theory is found in the coincidences it predicts.
Coincidences.
Yeah, like when things intersect in space-time, like when two particles collide or when an atom emits a photon. Those are coincidences.
So he's saying the specific arrangement inside the whole doesn't really matter as long as those observable events, those coincidences, stay the same.
Exactly. And since those coincidences are preserved even after these whole transformations, it's kind of like they're just different ways of describing the same physical reality, different mathematical perspectives on the same thing.
I see. So Einstein basically found a way to reconcile substantialism with the whole argument by shifting the focus. He emphasized what we can actually observe, the empirical content of the theory, instead of getting bogged down in, abstract math.
That's a great way to put it. He sidestepped the issues of indeterminism and unverifiability by grounding his theory in what we can actually see and measure.
This is also fascinating. It really makes you think about the relationship between our scientific theories and, like, our philosophical interpretations of them, and about the nature of reality itself.
It really does, and that's the beauty of the whole argument. It forces us to confront these really deep questions about what we can know about the universe and how we can know it.
But for our listener, the philosopher who's trying to make sense of all this, what would you say is the key takeaway here? What should they be thinking about after listening to this deep dive into the whole argument?
Well, I think the biggest takeaway is that we shouldn't assume that our scientific theories are like literal pictures of reality.
Yeah, it's tempting to think that, right? Like every equation and every symbol means something concrete out there in the universe.
But the whole argument it shows us that might not always be the case. Sometimes, those mathematical structures are just tools. They're like scaffolding that helps us understand how things work.
Oh, I like that, right? So the real challenge is figuring out which parts of the theory are actually describing reality and which parts are like just convenient fictions.
Exactly. And that's a pretty deep philosophical question.
It is. It reminds me of trying to interpret a philosophical text. You can't always take metaphors literally. You have to look for the deeper meaning behind them.
Absolutely. It's about understanding the concepts, not just the words. And the whole argument, it highlights this tension between the way we use math to describe the universe and the actual nature of reality.
Yeah, it makes the wonder, if we can't always take our scientific theories literally, then how do we decide which parts to take seriously?
That's the million-dollar question, right? It's a question that philosophers of science have been wrestling with for ages.
Where do we draw the line between what we can actually verify through observation and what's just a useful theoretical tool?
Right. And the whole argument, it really pushes us to confront that question head on.
Because it suggests that even our best theories, even something as successful as general relativity, might contain parts that are purely mathematical, like they don't actually correspond to anything physical in the universe.
Exactly. And I think it's a call for humility. It reminds us that even our most sophisticated models of the universe are just that, models.
They're representations of reality, not reality itself.
Right. And we have to be mindful of that. We have to acknowledge the limits of what we can know.
And be open to the possibility that there might be things out there, mysteries of the universe, that our current theories just can't explain.
Exactly. So as we wrap up our deep dive into the whole argument, I think the most important thing to remember is to keep asking questions, to keep challenging our assumptions, and to keep searching for those deeper truths about the universe.
Well said. It's been a fascinating journey exploring this mind-bending concept with you. And for our listeners, I hope this has sparked some new ideas and maybe even some healthy skepticism about the way we understand the world around us. Keep exploring, keep questioning, and keep diving deep. Until next time.